In Module 6, Section 1, we introduced composition of functions and finding inverses of functions. So when you're finding a composition of two functions, what you're doing is evaluating a function with another function. So previously, whenever we evaluated an equation, we've plugged in a number for x to find out a y value. But now, what we're going to do is plug in an equation for a variable and get an equation out. Okay. We also talked whether or not a function is one-to-one. And the way we can check it, well, the best way to check it is to graph it on Desmos and determine if it passes the horizontal line test, which means if a horizontal line is drawn through the graph, it only touches in one place. Then you know if the function is one-to-one. We also checked how to determine if two functions are inverses of each other. And the way we determine that is we find both compositions, f of g of x and g of f of x, and see if they both equal x. And then the last thing we talked about was finding the inverse of a function, which is when you set it equal to y, you switch x and y, and then you resolve for y. So in our examples, I'm going to start with composition. So in the first problem, we're given the equations f of x is 2x minus 1, and g of x is x squared plus 4. And we want to find f of g of x and g of f of x. So one of the things I always tell students, the easiest way to determine how you're going to plug in equations is that the second equation always plugs into the first. So I'm finding f of g of x, g is going to plug into f. So another way, so typically you write it with the little circle, but another way you can write it is f and then parentheses g of x. Both of those mean the same thing. So the way I'm going to start is I'm going to start with my equation f, and it starts with 2, so I'm going to write 2. Now instead of rewriting x, what I'm going to do is replace it with my function g. So it's going to become in parentheses x squared plus 4, and then minus 1. Now I'm going to go ahead and distribute the 2 into the parentheses, and we're going to get 2x squared plus 8. And then we still have our minus 1. And the last step of the composition is to combine like terms, if there are any. And we get 2x squared plus 7. And then there's our final answer. It's important to indicate that when we're finding a composition, we're not multiplying the two equations together, and we're not going to have 2x times x squared plus 4. We're replacing the x instead of just multiplying it. So the second example we're going to look at is g of f of x. So in that case, f is plugging into g. So we can write it g of f of x. We can also write it g and then in parentheses f of x. So our function g starts with x squared. So what I'm going to do is I'm going to start by taking my function f, 2x minus 1, putting it in parentheses, and then squaring it. And then we're going to continue with our plus 4. It's important to remember here that when we have 2x minus 1 squared, we have to expand it. So it becomes 2x minus 1 times 2x minus 1, and then the plus 4. Now I have to distribute, so 2x times 2x is 4x squared. Then we get minus 2x plus 1, and then we still have our plus 4. And then just like when we did f of g of x, the last step is to go ahead and combine like terms. So we're going to get 4x squared minus 4x plus 5. Okay. So we can see here that when I did f of g of x and g of f of x, I did not get the same answer when I did each composition. So it's important to note that the order of the composition does matter. So f of g of x and g of f of x are not the same and they won't result in the same answer. So it's important you can identify how to plug in the equations for each. The next thing I'm going to take a look at is determining whether two functions are inverses of each other. So we're given the equations f of x is 2x minus 1 and g of x is 1/2 x plus 1/2. So when we're checking this, what we do is we're going to find f of g of x and then g of f of x, and we're going to make sure both of them simplify to x. So I'm going to start with f of g of x. So we're going to have 2, and then I'm going to replace the x with my second equation, g, which is 1/2 x plus 1/2. Next, I'm going to distribute the 2 in the parentheses. So 2 times 1/2 x is just going to give us 1x. And 2 times 1/2 is going to give us 1. So we end up with 1x plus 1. Oh, I forgot the minus 1. And then I should still have the minus 1. And now I'm going to combine like terms. So I get f of g of x equals just x, because the plus 1 and the minus 1 will cancel out. So far, so good. However, I still have to check the second composition. Checking just f of g of x is not enough to say whether or not the two functions are inverses of each other. So when I'm checking g of f of x, start off with my function g, which is 1/2. And then instead of x, I'm going to have my equation f, which is 2x minus 1. And then outside the parentheses, we still have the plus 1/2. So I'm going to distribute the 1/2 into the parentheses. 1/2 times 2x is going to be 1x minus 1/2 times 1, which is 1/2, and then plus 1/2. So when I combine like terms, I'm left with x. So because both compositions simplified to x, we can say yes, they are inverses. The last thing we're going to take a look at is finding the inverse of a function. So it's a pretty easy 3-step process. All right. So we have f of x equals 3x minus 5. So the very first step is to rewrite it as y equals. So we're at y equals 3x minus 5. Next, we're going to switch x and y. So we get x equals 3y minus 5. So what an inverse does is in the original equation, you plug in x and get out y. In the inverse equation, the x value you plug in should result in the y value from the original equation that you plug in results in the x value from the original. So when I switch x and y, that's pretty much the base of an inverse. It's just switching x and y. But we don't leave equations as x equals. We write them as y equals. So once I switch x and y, I then work on getting y back by itself again. So I'm going to add 5 to both sides. I get x plus 5 equals 3y. And then I'm going to divide by 3. So it's important that you use the correct notation for inverse. So whatever your function is, which in this case is f, we put a little -1 next to it and then an x, and that indicates it's in the inverse. And then I can leave my answer as a fraction. I can leave it as x plus 5 all over 3. You can, if you want, break it up. You can write it as 1/3 x plus 5/3. That is acceptable. It is the same thing, but you're not required to split it up into a fraction. In our second example, we have g of x equals 1/2 x plus 9. So again, first step, rewrite it as y equals. So y equals 1/2 x plus 9. Okay. Next step, switch x and y. So we get x equals 1/2 y plus 9. And now I'm going to work on getting y by itself. So I'm going to subtract 9 from both sides. So we have x minus 9 equals 1/2 y. Now, the way we want to get rid of that 1/2 is typically we would divide by the number in front of y like we did in the first example. But the number in front of y is a fraction. So instead, we're going to multiply both sides by its reciprocal. So the reciprocal of 1/2 is 2. So I'm going to go ahead and multiply both sides by 2 because 1/2 times 2 does equal 1. So 1/2 times 2 equals 1. So that means that y is by itself now. So my inverse, g with the inverse of x, equals, and I am going to distribute the 2 on the left side into the parentheses. And it's going to become 2x minus 18. So please reach out if you have any questions about compositions, determining if two functions are inverses of each other, and finding inverses.